Dear student and friends, I am Dr.Abdus Sattar, HOD Department of Physics, SKMU, Dumka. In my previous lecture, I have said about something operator, little bit about operator. Now I want to discuss about the properties and the commercialization of that operator. Yesterday I have said that when any function write like that, if A is operator and that operator in a function, then it give the function unchanged and give a constant value that is called eigenvalue. So this mainly concept here wave function may be changed, but we are interested only that case where wave function does not change. In quantum mechanics we can use only this property that is called eigenvalue, eigenfunction property. In any operator, when A operate on a wave function and B another operator operate on a wave function and this give the same value, same eigenvalue and same condition, then that case A can be write as B. That means A and B are equal operator. Similarly, when we add up the two operator on a wave function and whatever the value get and then apply on a single wave function C and get the same eigenvalue, in that case we can write C equal to A plus B. So in this way it can be follow the associative law and distributive law. In quantum mechanics we are interested some special function that we can use like position, and operator form it can write like x operator equal to x. Another momentum operator that can write as p into minus I cross del x, and Hamilton operator p square by 2m plus v, that means minus h square by 2m del square v plus v. So and energy also we can write like this, E equal to I h cross del t. And another also function we can find out the angular momentum function also there. In that case we can discuss a little bit after that lecture. So we are interested only for the commutation relation of this operator. So when it is like a commutator form, then it can write like this, x p within third bracket, and it can be find out as value xp minus px. So when we find out this type of commutation relation, then we always use an wave function psi. Here write like this, x into p psi, and that can write x p psi minus px psi. Now we put the operator value of position and momentum like that, x into minus I cross del x psi minus I h cross into del x psi into x psi. So when operate these things we can write this way, minus I cross x del psi by del x, similarly minus into minus plus, and I h cross into x, first unchanged and operate on that one, and second case this is unchanged and operate on this one, and then we get the values. So this is positive and negative and positive, so cancel out, only we get the minus I h cross into psi. That we can write x into p equal to I into h cross. Here x and p does not give the value, zero value, so we can say this is not a commute. Each other not a, this is a non-commute. If it is 0, then we can find out it is a, if it is 0, then we can say these both are in commutation relation. Now I want to discuss the commutation relation between the momentum and Hamiltonian. So this again we can write like this, momentum p operator and h operator commutation from and operating on the psi function, then this can write as p h psi minus h p psi. Now we put the operating value of momentum and Hamiltonian, then we can write like this, minus I h cross del x minus h cross square by 2m del 2 by del x square plus v into psi minus of minus x square by h square by 2m del 2 by del x2 plus v and minus I cross into del x into psi. If we take only the free particle system, then that case v equal to 0, so we can put v equal to 0 here and also here. Then we can operate this on that, then we can get like this, h cross I cross h cube by I h cube by 2m into del by del x of del square by del x square into psi minus I h cross cube divided by 2m del 2x by del x square into del x of psi. So when operate this on, then you can get del cube, or this del cube psi by del x cube, and here also we can find out the del cube by del square. So both are the same function. So this is equal to 1 minus and this will be equal to 0. That means momentum is commute with Hamiltonian. So this is very important case in our quantum mechanics. Of any function, any operator, if commute with the Hamiltonian, then we can say this is your constant of motion. So in this we can also find out the operating system and about the angular momentum. So in case the angular momentum, we can write like that: L equal to R cross P. R is the position vector and P is the momentum vector, L is the angular momentum vector. So in vector treatment, in determinant form, we can write like this: I, J, K, X, Y, Z, P, X, P, Y, P, Z, and then we can evaluate this one, and only the component, we can take the only component, then we can find this one, Lx equal to Y, P, A, Z. Yeah, so we take the component, so Y, P, Z minus Z, P, Y. Right, like this. Similarly, you can find out Ly and Lz. When we put the value operating system on that P, then we can write like this: Y, and this is equal to minus I H cross into, yeah, this is on del I H minus I H cross में del Z. So this is one, and here also we can write like this one. Similarly, Y, Ly we can write like that, and Lz we can write this one. Now we will find out the commutation relation between the position vector and the angular momentum. When both are in the same component, Lx and x, when operating this one, then you can also write like this: Lx xi minus x Lxi. Then you can put the value of Lx like this from here. This one you can put this one, and for this one you can also put this one. Now we take the operating system of that system. When x and psi, when you operate that, if you remove the psi also, you can remove. Then when y del x by del z, this is the other function, other variable, so it will be 0. For this case also, solve this whole equation, then ultimately we can find out this is equal to 0. That means x is commute with Lx. But if we take the another component like y, Lx into y, then you can write minus h cross में y del x minus z del y into psi, or minus h cross y into y del z minus del x. In this case, when y is the derivative for this value, we can get only the z here. When operate this one, then it can be z value, but here for this, when operate this way del y by del z, that means 0. But for this case, we can give value only z. Similarly, here also, when operate this one, this is equal to 0. So this can be right on the minus h cross में 0 minus z into 1, that is equal to plus I h cross Lz. So when we take the commutation relation between the angular momentum with the another component, another Cartesian component, then we can get the third component of that value. Similarly, you can write Lx Lz, that we can find out the I h cross y. So in this way, you can also find out the details commutation relation of different operator like that. In this way, if we take the commutation operator between Lx and Ly. Now I want to find out the eigenvalue and eigenfunction of Lz function. For this, you can write Lz operator in polar coordinate system. When you use in the polar coordinate system, then Lz can write like that: minus I h cross del psi. So in operator technique, Lz operating with psi, then we can get eigenvalue and that function, this is c into psi. So find out, putting the value of Lz in polar coordinate like this: minus I h cross into del phi equal to psi equal to c pi. Now we solve this equation. First, we can take this way: del psi by del phi equal to minus c by h cross into psi, and then again we take the psi divided by this one, d psi by d, d psi by psi equal to minus c by I h cross into d phi. And integrating that one, we can get the logarithm term, and ultimate value we can find out psi equal to this one. It will be I c phi into h cross, and some function, constant function, and that vary with the radial and azimuthal part of this wave. So if this wave is valid for any type of body, so when we using the Bloch's theorem in solid state physics, in that case, when the value is phi and again for 2 phi, the value does not change. So in this way, we can write this one f r theta e to the power minus I c phi equal to f r theta e to the power minus I into phi plus 2 pi divided by h cross. So when we using this property, then we can write as e to the power I c into 2 pi by h cross should be equal to 1. And solving that on, we can get c into 2 pi by h cross equal to 2m into phi. That means c equal to m pi. That is the eigenvalue c, m is integer and h cross. So in this way, this is the eigenvalue of Lz function. So when we put this value on the wave function psi, this one, then we can write as psi equal to f r theta e to the minus I into m into phi. Now again we find out the constant function r theta phi using the orthonormal condition of the wave function. So on that case, if we apply that on condition, then we can get this function should be realized by 1 by root over 2 pi. So that is why psi can be ultimately write as 1 by root over 2 pi e to the power I into m phi. So this is the eigenvalue of the Lz function. That's all the total topic about the operator technique. Thank you.